Okay, guys, so we do have a 6.2a, 6.2b. It's only split up because there's a worksheet A and a worksheet B. We're going to do both today. So you can just title it 6.2, Apply Properties of Rational Exponents, because they're both the same. We're just working with different rules. So before we start looking at examples, we do need to write down the properties of radicals. And both of these, we have a multiplication and a division property. Both of them are things that we've been using before, but with square roots. So now we're just applying them to general nth roots. So if we have two numbers inside the root being multiplied, we can break that up. And it also works the opposite way. If our index is the same, we can multiply those two roots together. Okay? And it would all end up underneath the radical. Same type of idea goes for division. If we have a fraction inside of the nth root, we can break it up to the nth root over the numerator and the nth root of the denominator. The only thing we have to remember is that if we want the index to be the same, so we have to make sure that we write the index the same as what the original problem has. One thing we do have to write, just to cover our bases, is that b cannot equal 0. And the reason being is because we can never have 0 in the denominator ever, because that will give us an answer of undefined. Okay? So we just have to specify that b cannot equal 0. Now, example number 1. So we have the fourth root of 625 times x to the 8th times y to the 4th times z to the 12th. Now, the reason why I showed you all of the rules first is because for this one, I want to start by separating each individual term. So this is going to be the same as... So this is going to be equal to the fourth root of 625 times the fourth root of x to the 8th times the fourth root of y to the 4th times the fourth root of z to the 12th. So all I did for this first example was break everything up so that we can figure out what's going on, and then later we won't have to break it up anymore. But I just want to show you what's going on. So we can break each individual term up and take the fourth root of each one individually. So 625, that's the same as saying what to the fourth power? What times itself 4 times is going to give me 625? 5. That's the same as saying 5 to the fourth power, right? So what would the answer be? The fourth root of 625 is 5. Now let's look at this one. The fourth root of x to the 8th. So I'm thinking, what times itself 4 times is going to give me x to the 8th? X squared. What about the fourth root of y to the 4th? What times itself 4 times is going to give me y to the 4th? Y. And then what about z to the 12th? What's the fourth root of z to the 12th? Z to the 3rd. So that would be our answer. So we don't have to break it up each time. I just wanted to show you that we're taking the fourth root of each individual one. Did anybody find a pattern? How did we get the fourth root of x to the 8th? Did anybody find a shortcut for that?
Divide 8 by 4?
Yeah, we can divide the exponent by the index. So let's write that note off to the side. Divide the exponent by the index. So dividing the exponent by the index, that's how we can get what exponent we have left. Why does this work? Let's take the fourth root of x to the 8th, just to look specifically at one term. On Friday, we practiced going back and forth, right? How would I rewrite this one as a an exponent as a fraction, where would that 4 go? The numerator or the denominator? The denominator. So this is the same as x to the 8 over 4. Does everybody agree with that? How does 8 over 4 reduce? 2. So this is the same as saying x squared. Isn't that what we got down here? So that's why it works. Okay, because if we rewrite it in rational exponent form or notation, we could reduce a fraction and still get the same answer. So that's why it works. Okay, guys, example 2. We are taking the cube root of 27a squared, b to the 7th, c to the 4th. I'm not going to break it up this time because it makes for a lot of extra work. But what I do want us to get used to is writing the numbers in terms of primes to powers. So how could we break down 27?
3 to the 3rd power.
It's 3 to the 3rd power. So this is the same as the cube root of 3 to the 3rd, a squared, b to the 7th, c to the 4th. Now in this specific example, it all happens to work out. The reason why I want you to start doing this is for the examples when it won't work out. So I just want us to get used to it now.
How does this work out?
So now we can take the cube root of each term individually. So what would be the cube root of 3 to the 3rd? 3. So this is 3 on the outside. What about the cube root of a squared? Can I take the cube root of a squared?
2/3.
It'd be a to the 2/3, but can I pull it out of the root?
No.
No, because there's not enough. What about the cube root of b to the 7th?
I don't think so.
Not all of them. Could I pull out anything?
Yeah.
Yeah, how many?
3.
3, which would turn to b to the
Second.
2nd power. So how many b's are left inside?
So is there a parentheses?
Well, we're not there yet. If I am taking the cube root of b to the 7th, I can pull out a b squared. How many b's are left inside of the root?
1.
1. Well, let's think about it. What's 7 divided by 3? 2, remainder 1. So we can pull out 2, b squared, but there's a remainder of 1, so it has to stay inside. What about c to the 4th?
1.
1c, and how many are left over? 1, right? So inside the cube root, and this is why I'm saying make sure you write the index inside the root, because it could very easily look like a c to the 3rd, right? So make sure it's inside the radical symbol. What was left inside?
8.
We didn't pull out any of the a's. We had to leave 1b in there, and we had to leave 1c. Because we're pulling out groups of 3, right? And I have 4 c's in here, so I can pull out 3 of them, but there's still 1 left over. And that's my answer. So it's similar to what we were doing in the previous unit with square roots. But with square roots, we were looking for pairs. With cube roots, we're looking for groups of 3. With fourth roots, we're looking for groups of 4. So it all depends on what your index is. Okay? All right, example 3. 15 over the 4th root of 27. Okay, remember how before we can't have zeros in the denominator, we can't have i's in the denominator, and we can't have roots in the denominator. So am I allowed to have a 4th root in the denominator? No. Can you please write yourself that note? No roots in denominator. Okay, we can't have roots in the denominator. So we have to rationalize the denominator. But the process is a little bit different for nth roots than they are for... The idea is the same, but it's a little different for nth roots. So, what I want us to do first is we need to write 27 in terms of exponents. So this is 15 over the fourth root. How can I write 27 in terms of prime exponents? 3 to the what power? 3 to the third power, right?
Yeah.
How could I figure that out? We could break 27 down to 9 and 3, and 9 breaks down even more to 3 and 3. So we have 1, 2, 3 threes in there. So this is 3 to the third. Is everybody okay with that? Okay. So let's think about this. How many 3's do I have to have inside that radical in order for the fourth root to go away?
4.
How come 4?
There's 4, 3.
Because it's a fourth root. We're looking for groups of 4, right? So how many 3's am I missing?
1.
Just 1. So multiply the top and bottom by the fourth root of 3. Because that rule that we wrote out at the very beginning says that I can multiply as long as the index is the same. So on top, that's going to give me 15 fourth root of 3 all over the fourth root of 3 to the third times 3 gives me 3 to the
4.
fourth. And now what do you guys see that I can do?
I can pull it out.
Pull it out. So this is the same as 15 fourth root 3 all over 3, because that index and the exponent cancel. And can I simplify it all?
Yes.
Yeah, 3 goes into 15 how many times? 5. So this is 5 fourth root of 3. It's not a square root, it's still a fourth root, so you still have to write the fourth root. But we can simplify the coefficients. Okay guys, example 4. We cube root of 3 over 4. Now this goes right back to one of the rules we wrote at the beginning. The very first thing we want to do is break this apart. So this is the cube root of 3 over the cube root of 4. Okay, I have a cube root in the denominator, which is not allowed. So before I start trying to rationalize or get rid of that denominator, I need to figure out how I can rewrite 4. 4 breaks down to 2 and 2. So this is the cube root of 3 all over the cube root of 2 squared. So all I did was I rewrote 4 as 2 to the second power.
That's really hard.
Okay, because I am taking cube roots here, how many 2's do I need inside in order for it to cancel out? 3. So how many am I missing? 1. So multiply the top and bottom by the cube root of 2.
Oh,
Okay. Can I multiply inside the roots?
no, yeah.
Yes. Why?
Because they're both to the third power.
Because they are both cube roots. So this is going to be the cube root of 6, 3 times 2, all over the cube root of 2 to the third. 2 squared times 2 gives me 2 to the third. Equals. Cube root of 6 can't simplify at all, so it is the cube root of 6 all over. What's the cube root of 2 to the third? 2. Can I reduce 6 and 2? No. 6 is inside the radical, so it cannot be reduced by 2. 2 is an integer, 6 is not. So this is our answer. Okay, example 5. We have 2 over the fourth root of 8. All right, guys. We are not allowed to have a fourth root in the denominator, correct? So I first need to rewrite 8 into as many primes as I can. How does 8 break down? 2 and 4 and 2 and 2. So this is the same as 2 over the 4th root of 2 to the 3rd. If I have a 4th root, how many 2's am I missing? 1. So let's multiply by the 4th root of 2. So on top, what does that give me?
2
2 to 4th root 2 all over the 4th root of 2 to the 4th.
equals
So that's 2 times the 4th root of 2 all over.
2, and then you can simplify.
What's the 4th root of 2 to the 4th? 2.
And then you can simplify.
And then I can simplify. 2 goes into 2,
And then you're wrong.
1.
And then I slapped you across
So that gives me the 4th root of 2.
You know that, right?
3x to the negative 1/2.
I thought you could have one of those
I know. Why would it stress me?
Okay. So, first of all, we have something that is not allowed. What is it?
X.
Negative exponent. So, what do I have to do with that negative exponent? Bring it to the bottom. Does the 3 move anywhere, or does it get to stay? It stays. So, this is 3 over x to the positive 1/2. What root am I taking when my exponent is 1/2?
Cube root. It's
Cube root means 3. What means 2?
Oh, I mean the square
It's
root.
the square root. So that's 3 over the square root of x.
I thought it was right.
Okay, if I'm taking the square root of x, how many x's do I need in order to cancel with the square root?
One more X.
Well, how many total?
2.
2, right? So how many am I missing?
1.
1. So multiply top and bottom by the square root of x. That's going to give me 3 square root x all over the square root of x squared, which is 3 square root x over, what's the square root of x squared?
X.
X. I can't reduce any more, so that is my answer. All right, example 7. All right, number 7, cube root of 2 all over negative 3, cube root of 9. Okay, first of all, let's rewrite 9 so that we have it in terms of exponents. How can I rewrite 9 in terms of exponents? 3 squared. So this is the cube root of 2 all over negative 3 times the cube root of 3 squared. How many 3's am I missing to get rid of the cube root of 3 squared? Just 1. So multiply the numerator and denominator only by the cube root of 3. In the numerator, I have the cube root of 2 times the cube root of 3. Can I multiply those together?
Yes.
I can, because my index are the same. So this would be the cube root of 6 all over negative 3 times the cube root of, what's the cube root of 3 squared times 3? 3 to the 3rd. 3 squared times 3 gives me 3 to the 3rd. Okay, so this is the cube root of 6 all over Negative 3 times, what's the cube root of 3 to cubed? 3. So this is negative 3 times 3. This is a common mistake I saw on the test. A lot of times when you guys pull out of the root, you made it an addition or a subtraction. It's all multiplication unless there's already a sign there.
It would have been subtracting, wouldn't have been undefined.
So, well, it's multiplication. So this is the cube root of 6 all over negative 9. You can't reduce anymore because the 6 is inside the root, so that's it.